This video presents a generic experimental procedure. Please consult your class notes for term-specific instructions. The lab setup for this experiment consists of a function generator, a power amplifier, a standalone speaker with an orange mounting stage, and several metal washers. Here's a block diagram of the system. LabVIEW controls the Keysight function generator, which outputs a sinusoidal signal to the power amplifier. The boosted signal passes through a shunt resistor, which allows us to measure current flowing to the speaker. The shunt resistor is valued at 0.1 ohm. By measuring the voltage across the resistor, denoted V2, we can calculate current using Ohm's law. The voltage at the speaker, denoted V1, is also measured throughout the test. The shunt resistor is physically located at the DAC chassis, mounted in a BNC to banana jack adapter. Here's a more detailed diagram of the wiring. This diagram is included in the student guide. Gently place a speaker on the PVC stand and connect the alligator clips to the terminals. Note the polarity: black to the negative terminal and red to the positive. Turn on the Keysight function generator using the power button. The boot up sequence takes about a minute. Turn on the power amplifier using the front button. On your desktop, open the X95 shortcut folder and select Loudspeaker Main Shortcut. LabVIEW may take a few minutes to load. Once the LabVIEW program is open, activate the Configuration tab. Navigate to the function generator port and use the pull-down to select the valid USB port to connect with the Keysight function generator. Next, verify the amplitude voltage is set to 0.03 volts and the units of magnitude is set to ohms. Click the Frequency Sweep tab to return to the main panel. In order to determine the various speaker parameters, you'll need to run a series of 6 different tests. First, we'll perform a coarse frequency sweep with the microphone to capture the general response profile. Click on the white arrow in the menu bar. The frequency sweep sequentially steps through a range of frequencies, which we'll set from 5 to 300 Hz with a large step size of 5 Hz. We'll use the default settings of 2000 milliseconds to ensure steady state and a repetition of 1. Now press the Take Data button to start the sweep. The various signals are plotted in LabVIEW along with the construction of the Bode plots, as the frequency is sequentially incremented over the defined range. The frequency sweep will take several minutes, so be patient. When the sweep is done, LabVIEW will automatically prompt you to save the data. Enter a descriptive file name and save to the desktop. Next, we're going to run a frequency sweep over a narrow range to better identify the resonant frequency. Use the previous results to identify a narrow band around the resonant frequency. Rerun the frequency sweep over the refined range with a small step size for improved resolution. In this example, the peak is between 75 and 90 Hz. Again, when finished, save the data to your desktop using a descriptive file name. We're going to repeat the last 2 tests, but with the addition of a mass on the speaker. Select between 1 and 3 metal washers, then measure and record the total mass. Remove the plastic wing nut from the orange stage. Install the desired washer mass onto the stage and replace the wing nut. Gently snug the wing nut to prevent the washers from rattling. Repeat the coarse sweep from 5 to 300 Hz with a large step size. Click the Take Data button when ready. Once again, we'll run a sweep over a narrow range to better identify the resonant frequency with the mass. Use the previous results to identify a narrow band around the resonant frequency. Rerun the frequency sweep over the refined range with a small step size for improved resolution. Here's a Bode plot with and without the mass. Use the shift in resonant frequency to determine mechanical mass and compliance of the speaker. Next, we'll perform a high-frequency sweep to estimate the inductance, denoted LE. Unscrew the wing nut and remove the metal washers used in the previous study. Reinstall the wing nut on the bare stage and snug gently. On the configuration panel, temporarily reduce the amplitude voltage to 0.01 and return to the main panel. Set the range from 500 to 3000 Hz with a large step size of 100 Hz or so. Press the Take Data button to run the test. Plot the imaginary component of impedance versus frequency with the units of rads per second. Use the best fit slope to estimate inductance. The final test is a low-frequency sweep to estimate the force factor, BL, and electrical resistance, RE. Navigate to the configuration panel and restore the amplitude voltage to 0.03. Then return to the main panel. Set the frequency range from 0.5 to 5 Hz with a small step size. Then click the Take Data button to run the sweep. Plot the imaginary component of impedance versus frequency with the units of rads per second. Use the best fit slope to estimate the force factor, BL. Use the asymptote of the real component of impedance to estimate electrical resistance, RE. Be sure to save your data before you leave the lab today.